Oh, hey there. So today I've brought you to this nice lovely desert to talk a little bit about the next type of force that we have to deal with. And rather than a specific type of force, it's actually a class of forces. What we're talking about next are resistive forces. Resistive forces are any type of force that resists the motion that an object is undergoing. It doesn't really care about what other forces are necessarily on the object. It can matter, but what really matters is the object moving, which direction is it moving in, and the resistive motion will always act in the opposite direction to the motion. So can anyone give me an example? Can anyone give me an example of a resistive motion? Something that always works against the direction of motion. I'm sure most of you came up with the idea of friction. And yeah, we're getting into friction for sure. But is there any other that you can think of? Air resistance is a really good one. As we travel in our atmosphere, whether we're on the ground or in the air, there is molecules in our air that are essentially acting to slow us down. And so whether we're running on a windy day, whether a skydiver has jumped out of an airplane, or even a bird flying through the air, they're flying through a medium. And by moving through the medium, there is a force in the opposite direction to the motion. We'll talk about air resistance or use air resistance at another time. Today, we want to focus on friction. Friction is super, super important in the way that we live on the surface of the planet. It is an imperative force in almost everything that we do, in the technology that we built, in the way that we naturally move around this planet. Anytime you have motion on the planet Earth, you probably have friction. You could come up with some times where friction can be neglected because it is very small, whether we're on what we consider a frictionless surface, like skiing on snow or skating on ice or something like that. But for the most part, not only do we encounter friction, we embrace it. We use it as part of the technology that we built. And it's interesting to think of this force. This is going to be a force whose sole job is to stop us from doing what we want to do, essentially, right? But it can be something that is very useful, as we'll see, for something as simple as driving a car. And so let's get into the idea of friction and this resistance to motion. Even friction is going to have two different kinds. So even we're subdividing resistive forces into air resistance. Even you could think of resistive forces in water, if you like. But focusing on friction specifically, there's even a couple of types of frictional force. Let's think about what those types of frictional force are. Well, we first mentioned that the frictional force, that is the definition of which wants to resist motion. Well, where is that force actually located? Well, if I was to give this chair a little bit of a push, it moves and then it comes to a stop. So I'll give it a little more of a push, moves, and it comes to a stop. Our frictional force on this chair is through the interaction of the wheels on the chair and the road itself. And the direction is going to be this way. If I'm moving the chair in that direction, the frictional force is working this way. And so let's look at a different type of friction, a type of friction that actually has to do with not moving. And you might be saying to yourself, what? I thought friction had to do with resisting motion. Yes, but it's actually resisting even the start of motion. So let's take this object right here. It is obviously not moving, and I want to get it moving. I want to get it started moving, and so I apply a force to it. Yet it doesn't move. I push it and I push it and I push it, but if I'm applying a force in this direction, if there's no other forces, that force should create an acceleration, F equals ma. But there is another force. There's a force that not only resists motion, but it resisting the beginning of motion. This is called the static frictional force. When you have an object like this that is not moving, that is static, and you apply a force to that object and it doesn't move, there's a static frictional force that is equal and opposite the force that you're applying onto it, and they balance each other out, and no acceleration occurs, no motion occurs. And that's what's happening in this incident right here. Can't do it, can't do it. And so that static frictional force is too hard. Now, once the object actually gets moving, then there's a different frictional force. That's called the kinetic frictional force. And there's a difference between the two of them. You never have both a kinetic and a static frictional force on the same object. It's if the object's moving, it's kinetic frictional force. If the object's not moving, it's static frictional force. So let's look at static frictional force in a little more detail. How do we increase the static frictional force? How do we make the static frictional force bigger? Well, think about why it would be harder to move this chair. So, to be honest, it's not hard for me to move this chair. It's very, very easy for me to move this chair. But let's say that we put something very heavy onto the chair. Let's add another 1,000 kilograms. 1,000 kilograms right there. Now, me trying to push the chair, it's going to be challenging. By increasing the mass of the object, the static frictional force clearly gets heavier and heavier. And so when we do derive our equation for the static frictional force, it is going to have to somehow take into account something to do with mass or maybe normal force, as we'll see. Okay, so then let's talk about kinetic frictional force in a little more detail. Again, kinetic frictional force only occurs when the object is actually moving. And so I can move this object, I can give it a velocity. Once it leaves my hands, it has a velocity, but that velocity quickly goes down to 0. It gets slower and slower and slower, and it stops. Once it leaves my hand, the only force on it in the horizontal direction is the frictional force, and it's acting that way. If the object's moving that way, once it leaves my hand, there's no force on it going that way, but there is a force going this way, and that's the kinetic frictional force, which eventually brings it to a stop. But what if we kept applying that force? What if we kept applying the pushing force? Then what does the kinetic frictional force look like? Well, now we're fighting each other, right? I'm pushing this across the road here, and we're battling one another, where the kinetic frictional force is going this way, my pushing force is going that way. If they were equal to each other, they're opposite to each other, but if they were actually equal to each other, then what happens is you get no acceleration, and we would actually end up pushing that at a constant speed in that direction. It's still moving, but no acceleration. Now, typically, I'm pretty strong, and so I have a force that's greater than the kinetic friction, and as I push it, I can still accelerate. So I can still accelerate as I push the chair across the road, but I still am countering that same frictional kinetic friction in that direction. I can overcome it. I can create a force that's greater than it in that direction, and then I will accelerate. But if there was no friction there, then I would be able to accelerate with a greater acceleration. So clearly, both of these types of friction depend something on how heavy my object is. Clearly, it is harder to push a heavier object than a lighter object because the frictional force resisting our motion will be heavier. We'll look into that. But I'm actually asking you a question to think about. Which force is stronger? If I'm defining the static frictional force and the kinetic frictional force as two separate things, which one is actually stronger? Let's think about it for a second. And you can do this little experiment yourself. Take something you have on your desk right now, maybe an eraser, if you have one of those big erasers, the pink ones or the white ones. Give it a little push, the tiniest little push you can imagine, until it just starts moving. And then think to yourself, is it harder to get something moving, or is it harder to keep something moving? Harder to get something moving, or harder to keep something moving? Let's give that a try. And so, again, I start by pushing this, and I'm just going to give it a little push, just one finger push. It's not moving, it's not moving, it's not moving. So I push a little harder, That's interesting to me. It seems to me that the static frictional force varies. The static frictional force is going to be equal and opposite the force that I'm pushing the object at. So if I push a little bit, then the static frictional force is a little. If I push a lot, then the static frictional force is a lot. And they combat one another until my pushing overcomes it. Once my pushing is strong enough that it is greater than the maximum static frictional force, then it will move. So here we go. So I push. Okay, I've got it. And now, now it's super easy. And what I've learned is that static frictional force, at least maximum static frictional force, is stronger than the kinetic frictional force. The kinetic frictional force will be constant the entire time, regardless of how far you push or how fast you push or what your force is, but the static frictional force will increase as you push harder and harder until you overcome it. But that maximum static friction seems to be stronger than our kinetic friction. So why is that? What's the difference between the two? Let's look at some equations. So now let's make a few notes about what we talked about and come up with some equations that are going to help us deal with resistive forces and specifically the forces of friction. And we define resistive forces as those forces that oppose motion, whether something is moving or wants to move, if you will, they're opposing that. And so the examples we had come up with were friction and air resistance, also commonly referred to as drag. We can think of others as well, but that'll do for now. And the one that we're most interested in, because we are dealing with usually things along the surface of the Earth, is the forces of friction. And specifically, there are two of them, and only one of these two frictional forces acts at a time. If you ever have an object and you're putting both forces on that object, you're doing something wrong. If it's moving, it's kinetic friction. If it's static, that is not moving, it's static friction. Let's start there with static friction. Call this 1. All right, and so as mentioned, static friction is our frictional force that's associated with resting, or I should say resisting motion for an object that is not moving, or for objects that are not moving. Now you might be asking yourself, does every object that is not moving have a static frictional force? And the answer is no, absolutely not. The only time you have a static frictional force is if there is a force being applied to that object in a direction that it would actually move if the static frictional force didn't stop it from moving. And so this table right here does not have a static frictional force associated with it. It's got our our gravitational force down, our normal force up, no static frictional force until I start applying a force to it. Start pushing that desk, then you'll get the static frictional force to appear. And so we need some new quantities to define these values. Let's start with static friction itself. And so this is our static friction force. And so notice that I used lowercase f on purpose there. That lowercase f refers to friction, s refers to static, as opposed to capital F, which we use for forces. And so the question is, what is the formula for static friction? Does it have a formula? And the answer is yes, kind of. The static frictional force is equal to, or I should say less than or equal to, this new constant multiplied by n, the normal force. This new constant is going to be very, very important. It's called the coefficient of static friction. It's given by this fancy letter u, which is our Greek letter mu. So we say Fs is less than or equal to mu sub s times n, where the s means the static frictional coefficient. And let's write that as well. So this is the coefficient, let's write it, the coefficient of static friction. And what that's going to depend on is the materials that are interacting. And so the coefficient of static friction is a quantity that defines basically how frictiony an interaction is. And so if you had skis over snow, that coefficient would be very, very small. But if you had like grippy basketball running shoes over a basketball floor, and you hear the squeak, squeak, squeaks of that, that would have a much higher coefficient of static friction. What else? This thing. Let's talk about this symbol here. That symbol means less than or equal to. Less than or equal to means that our static frictional force isn't necessarily equal to mu times n. It could be anywhere from 0 to mu times n. And it's all going to depend on what force is trying to make our object move. That mu times n is actually the maximum value that the static friction can be. That's basically the force you need to apply to overcome the static frictional force, or a little bit more than that, to overcome the static frictional force to actually have an object move. And so let's write a few of these things down. So let's say this value here, mu, depends on the interacting surfaces. All right, and then please note that the less than or equal to sign means that we can get as high as that value. In fact, why don't we write this, that Fs maximum, which is usually what we end up using in a lot of problems, is equal to mu s times n. Now, it would be a very specific problem where you would set your static frictional force equal to mu times n. It would be the kind of force like a question where you're just overcoming the force or just about to overcome the static frictional force. You'll get experience with that idea. Okay, so what else do we need? Let's draw one free body diagram. I want to make sure that we see how we use this not just mathematically as we see here, but in our free body diagram. So let's draw a free body diagram of that chair that I was pushing around the desert, right? So free body diagram of a chair, and let's do it when I was trying to push it, but it wasn't actually moving. So that is pushed, but does not move. Okay, why don't you give that a shot yourself? Feel free to pause the video at this point and draw me the free body diagram on this chair that we would have in the case of you or me trying to push a chair, it not moving on the surface of the earth. Go ahead and do that now. We'll take it up in just a second. Okay, I assume you've given it a shot. We'll start with the easy ones. Yep, the force of gravity is straight down. The normal force is straight up since it's always perpendicular to the surface. Here the surface is horizontal, and so our normal force is perpendicular to the horizontal, straight up. Okay, now what about the other ones? Well, it depends on which way we're pushing them. So let's say, I think I was pushing in this direction. Now, some people may want to draw the pushing force like that. You can't. You cannot draw the arrow going in towards the object. Now, it makes logical sense. You're like, well, I'm pushing into the object. But pushing into the object is the equivalent of pulling the object. And we want all our forces to be pointing away from the mass themselves. That's how we're going to be adding them up properly. So this is my pushing force. Even though physically I am pushing it from over here, that was me trying to push the chair. That doesn't look like a human, but I was trying to push it in that direction. And so all of these are vectors. We're left with one final force. And that force is equal and opposite to the force that is trying to move our object along the surface. The frictional force is always parallel to the surface. Even if my pushing force was weirdly down, like imagine I was pushing down like this, or I was pulling, kind of in an upwards direction. That doesn't matter. It doesn't mean that the direction of the frictional force will always be opposite that force. It will be resisting the motion due to that force, but the direction has to always be parallel to the ground. And so our frictional force is that way. You can throw in an axis if you like, but we're not going any farther with this free body diagram, so it's not really helpful for anyone. But just for completeness, we can add that. And so here the normal force is equal and opposite the gravitational force. The static frictional force is equal and opposite the pushing force. There is no net force and therefore no acceleration on this object. And so we can also write that the static friction is dependent on the mass of an object and the forces parallel to the surface. That kind of summarizes where the static friction comes from. Like we mentioned, if our object is more massive, then it is harder to push. And that means our static frictional force can be heavier because of this value right here, right? If the mass is larger, then Fg is going to be larger. If Fg is larger, then N is going to be larger, and we will have a stronger possible static frictional force. Of course, dependent on the force it's being pushed at as well. So the static friction is dependent on the mass of an object and the forces parallel to the surface. Static frictional force is dependent on the mass of an object and the force is parallel to the surface. That's good. The only other thing we should mention is mu. Clearly, the constant mu s, the coefficient of static friction, is going to increase or decrease the possible static frictional force. And so that is the materials that make up the interacting surface. Both sides. Okay, whew. I think that's good for static frictional force. The kinetic frictional force is used very, very similarly, except it has a constant value. And what I mean by that is it does not vary depending on what is happening with the other forces that are causing the motion necessarily. It doesn't care how strong the push is as long as it's moving. If it's moving, it will have a very, very specific value. But other than that, things are very similar. So we have our kinetic friction. And this is the frictional force opposing the motion of an object that is moving. All right. And it has a very, very specific formula, not a less than or equal to, but just that Fk is equal to mu k times n. So our lowercase fk means the frictional force, or the kinetic frictional force here is equal to our coefficient of kinetic friction multiplied by the same normal force. And so let's define this new value, mu sub k, as the coefficient of kinetic friction. All right. And so if we were to draw a free body diagram of this time the chair actually moving, and so this is again the same chair. So let's do the FBD. Let's make that a little neater, huh? So free body diagram of the chair being pushed and moving. Well, it looks exactly the same, except we change where we had our static frictional force into our kinetic force. But other than that, it's identical. Let's push in this direction once again. The kinetic friction is resisting that motion, but maybe it's not big enough to stop an acceleration and our object moves. And so there we go. And so now that we have the formulas for our frictional forces, we know at the appropriate time they come into play. We can add the frictional force to our list of forces for doing multi-force, multi-body force problems.